Hello, and welcome to my presentation about SynCom, the synthetic corona outflow model for the heliophysics community. My name is Valmir MoraesFilho, and I'm a grad student at Catholic University of America.
Let's talk about the motivations of our work. The first being related to the PUNCH mission. But what is PUNCH? It's the polarimeter to unify the corona and heliosphere. Its main science goal is to comprehend the global scale physical process from the microscale turbulence to the evolution of global scale structures that unify the solar corona and heliosphere. Solar physics studies the sun and the corona, and it comes primarily from remote science and spectral analysis. And heliospheric physics studies the solar wind and the interplanetary space, coming primarily from the in situ observations. PUNCH is here to connect the two areas of physics which will help us understand how the coronal structures become the ambient solar wind and also understand the dynamic evolution of the transient structures in the young solar wind. A bit more about PUNCH. It's that its field of view will range from 4 to 180 solar radii, which no other mission has ever been able to achieve. And its 4 instruments will improve the solar wind and CME measurements because of their combined polarized exposures. This mission is scheduled to be launched in October 2024. The main motivation for SynCom is concerned with flow tracking. In preparation to the PUNCH mission, we have a group focused on developing different algorithms to track and measure the speed of coronal outflow with uncertainties. However, we came to a realization that we could not compare or validate these algorithms. SynCom comes in hand not only for that reason, but also to assess the impact of noise to the algorithm's accuracy, and to extrapolate the altitude range, which will be similar to the PUNCH images. The flowchart on the right shows you how our model is structured. We use Gaussian waves as the main engine to generate perturbations based on the input parameters. One of the key features of this model is that it's based on previous solar corona observations. We extract statistical information from the physical phenomena in order to construct our synthetic image. We use the data from a special campaign ran by Stereo A Core 2 in April 2014, which captured the deepest exposure of unpolarized images. What is interesting about this data is that the long exposure revealed more details. These images also went through an intensive process of preparation done by Craig DeForest, where he was able to remove the smooth background, the stores, the blur motion, and also did a coordinate resampling. For further information about what processes Craig DeForest applied into the images in order to make it cleaner and flow-friendlier, go see his article. Here is an illustration of how coordinate resampling works. Craig transformed the image coordinate system from Cartesian to polar. For the purposes of this work, we changed how we organize this data from a stack of images at different time steps to a stack of images at different position angles. And that's what we call distant time plots. In order to mimic the transient and quasi-periodic behavior, we had to extract some information from the data. First of all, we looked for how the radio brightness behaves. By doing a linear fit of the mean brightness by the distance, we noticed that the data behaves like a power law of order of -3. As expected, it indicates that the brightness decays with distance. The second aspect of the data that we explored was frequency. We know that the sampling time was 300 seconds. So we took the signal from the lowest altitude at all times from each position angle in order to extract the detrended signal. Then we took its Fourier power spectrum and we looked for the second highest peak. This peak will contain the signal's frequency and will determine the amount of features that appears in the image at a certain position angle. After collecting the frequency for all position angles, we used the detrended power spectrum as a threshold to determine a frequency that characterizes the data. The last parameter that we explored was velocity. Here we are going to use the distant time plots. This type of image contains signals for each time step at a fixed position angle. The animation shows us that the signal is attenuated by distance, but its base level remains the same. For this reason, we decided to use the cross-correlation of 1D signals as our flow tracking algorithm. This method evaluates the maximum correlation coefficient and locates its corresponding spatial lag. This analysis provided us with a range of velocities that allowed us to produce our first synthetic images. Our model can also accept velocity measurements from other methods, as long as they can also provide us with standard deviation measurements. Each of the parameters that I presented to you today control a different aspect of the image. For example, the frequency controls how often a feature appears. You can see on the right that our model resembles a similar amount of features as in the real data. The velocity and velocity standard deviation control the inclination and the width of the features. The model's brightness behavior mimics the real data pretty well. And the noise level in the model is generated by a random seed and can be adjusted. Here is a side-by-side comparison of the two images so you can notice their similarities. As an overview, our model is generated by Gaussian waves with fixed parameters, which will control the different aspects of the image that are derived from real solar corona observations. It is important to note that we are not trying to reproduce the outflow dynamics one by one, but rather to simulate a pattern that it is statistically similar to real data. Our overarching goal is to create a software that can generate a synthetic corona outflow that will serve as a testbed for calibrating the different flow tracking techniques out there because of its predefined velocity parameters. As an ongoing effort, we have launched a flow tracking challenge during the second flow tracking workshop that happened in June of this year, where we have invited all flow trackers and enthusiasts to test their algorithms using our synthetic images. Today, we invite everyone in the heliophysics community to participate. We have created a page under the Catholic Universe website where you will find some synthetic images for you to test your algorithms. I have added here a QR code that will take you there. Stay tuned for new information that will come really soon on the website about our new features. Lastly, we would like to present to you an in-development work that we have that is the synthetic corona outflow image. It is a spatial type of image that is very commonly used by some flow tracking algorithms. The parameters we control now are the frequency for each position angle, the velocity that will make our features move not only upwards but also to the right. Their standard deviation will control the form of the feature, and we can also control the noise level and brightness behavior. This animation shows a comparison of the real data to our model, presenting us with great promise, but still with some room to grow. For example, one of the problems that we have to fix here is that the shape of the features should decrease with height. As for our conclusions, we created a model that is statistically similar to real corona observations. Although not implemented yet, our model can also incorporate radio acceleration. The SYNCOM objective is to serve as a calibrator of the different flow tracking methods. The initial results from our flow tracking challenge already presented a success on testing different algorithms. And as an initial analysis, our spatial images show great promise on emulating the solar corona outflow. For our next steps, we are going to fix the known problems on the spatial images, such as the geometry features. Thank you for watching, and if you want to know more about SYNCOM, stay in touch and send me an email at moraesfilho@cua.edu.